Hi folks, this is the first video in a mini course on thermodynamics. Let's start with a gas. This gas is confined to a cylinder and the cylinder has a freely movable piston. Now the gas will exert a pressure, it will exert an upward force on the piston. So to keep the piston from flying off, let's put some sand on top of the piston. Now I could put some weights on top of the piston, but the whole idea of putting sand is that I can add sand in small amounts and remove sand in very small amounts, thereby changing the weight on the piston by very small amounts. So now let's say we have n moles of a certain gas. Maybe it's oxygen, or it may be helium, a monoatomic gas, or it may be methane, a polyatomic gas, whatever. There are n multiplied by Avogadro's number of molecules. Now, what are these molecules doing? They are whizzing around, bouncing against each other, bouncing against the walls, the cylindrical walls of the container, and bouncing against the piston. Now, each time a molecule bounces against the piston, it delivers a tiny amount of momentum. But there are zillions upon zillions of collisions happening per second, and all these tiny momenta add up to a fairly steady amount of momentum being delivered per second. So the momentum delivered per second is the upward force. Now that force balances the weight of the piston and the weight of the sand. So the weight of the piston plus the weight of the sand is equal to the pressure multiplied by the area of the piston, the cross-sectional area of the cylindrical container. Supposing I want to describe the state of the gas. Now one way of describing the state of the gas is to describe the position of each of the molecules and the velocity with which each molecule is moving. And of course, I would probably need to talk about whether each molecule is in the ground state or an excited state, whether it is spinning or whether it is vibrating. All these details, that means per molecule, we are going to have to give a large number of numbers. If it's just helium, and let's say all the helium atoms are in the ground state. So that means there is no rotation, there is no vibration, it is just whizzing around. Even then, per helium atom, I would have to give 3 numbers to locate its position, x coordinate, y coordinate, z coordinate, in some coordinate system, and the 3 components of its velocity, vx, vy, vz. That means I need to give 6 numbers per atom. So that means we are talking about 6 multiplied by Avogadro number multiplied by n, the number of moles. That is such a large number of numbers, but if I give you all those numbers, that is describing what is called the microstate of the gas. Now from this microstate, if I give you those numbers, I assure you, you do a simple calculation, the number of pages these numbers would fill would amount to, it will go well beyond our solar system. And if I give you that and ask you to find the pressure of the gas from that, you wouldn't be able to do that. In other words, this is a detailed description that's pretty useless. And if I had to use this data from which, using Newton's laws of collision, etc., to calculate how the gas evolves, that is how each molecule moves, that's going to require computers the size of galaxies. Instead, we ask ourselves, is there a simple macroscopic description, that is an overall average description for the gas? Instead of giving details about each molecule, can I talk about the overall average? The answer is yes. It turns out that this gas can be described by just 4 numbers. The 4 numbers are pressure, the volume, the temperature, and of course the number of moles. And of course we have to say which gas it is, whether it's helium or oxygen or nitrogen or methane or whatever it is. But given the gas, we need these 4 numbers to describe the state of the gas. When we talk about the state of a gas, we are talking about the equilibrium state of the gas. Let me explain that. First of all, what is the meaning of the word pressure? Right? There is air in this room, right? And if I say the pressure at this point is 1.01 multiplied by 10 power 5 pascals. So the units of pressure are pascals. So let's get that out of the way. So 1 pascal is going to be equal to 1 Newton per square meter. That is the units, SI units for pressure. So when I say that the pressure at this point, let's say, is 1.01 multiplied by 10 power 5 pascals. What does it mean? It means that at this point, if I imagine a surface, a flat surface, right? Imagine this flat surface. I have this cardboard, but I'm placing it here so that you can see it. But imagine any flat geometrical surface. Now the gas on this side will exert a force on gas on that side. And the gas on that side will exert an equal and opposite force on this side. And this force comes about due to collisions. Now it is very easy to show, but we won't be showing it in this course, that the net force exerted by the gas on one side is perpendicular to the surface, no matter how the surface is oriented. That force divided by the area is the pressure, average pressure over this area. Now shrink this area down to an infinitesimal amount dA about this point. You will find that the force is also infinitesimal. So the infinitesimal force divided by the infinitesimal area will give you the pressure at this point. In other words, we find the force divided by the area. The limit of that, as the area shrinks to 0, will give you the pressure at a point. So pressure can be defined at a point. Now, is pressure a scalar or a vector? It's a scalar, but the force is a vector. How do we understand that? Now, you see, if I imagine my surface here like this, oriented like this, the force is going to be perpendicular. The force has a direction. It's a vector. The force is now calculated using the number called the pressure multiplied by the area. If I now reorient the surface differently, what about the force on this surface? Again, it's perpendicular to the surface and it is a vector. It has got a direction. It's calculated using the pressure multiplied by the area. So you see, the force gets its direction from the orientation of the surface. In other words, I am sitting in this room. The force on the roof due to the air in this room is upward. The force on the floor is downward. The force on that wall is in that direction. The force on this wall is in that direction. It's calculated using a simple number, the pressure. The pressure is a scalar. You calculate the pressure by taking the magnitude of the force and divide it by the area. Okay, so that's pressure. What about the volume? The volume is measured in SI units. It's measured in cubic meters. Now, I'd like you to remember that 1 cubic meter is quite a large amount of volume. It contains 1000 liters. That means it contains 10 power 6 or 1 million milliliters. We'll be using all these numbers. So in SI units, volume has to be measured in cubic meters. Now, what is the volume of a gas? The volume of a gas, by definition, is the volume of the container. Even if the gas is just one molecule in a container, the volume of that gas is the volume of the container. What if I have a mixture of gases? Let's say 3 moles of methane and 2 moles of helium. The volume of the 2 moles of helium is the entire volume of the container, and the volume of the methane is the entire volume of the container. That's the definition of volume. Temperature. For the moment, let's just take the temperature as something that a thermometer measures. So let's put a thermometer through a hole in this cylinder. The hole is nicely sealed, right? So that no gas can escape. And we have a thermometer. So the temperature for the moment is something that a thermometer measures, and the units of temperature are going to be Kelvin. In other words, 0 degrees Celsius is 273 Kelvin. I'm ignoring decimal places. 100 degrees Celsius is 373 Kelvin, and so forth. And small n, of course, is the number of moles. So we need only these 4 numbers to describe the state of a gas. So we have these 4 variables which completely describe the equilibrium state of a gas. The question is, are these 4 variables independent? What does that mean? It means that can we assign values to these arbitrarily? Imagine, for instance, you go to a neighborhood shop where they are selling gas. You take a 2-liter container, which is evacuated. You go to the lady at the shop and ask her to fill it with 3 moles of oxygen at a temperature of 300 Kelvin, and you want the pressure to be 1.01 times 10 power 5 pascals. So in other words, you're specifying the volume, you're specifying the number of moles, you're specifying the temperature, and you're specifying the pressure. The lady pulls out her calculator and goes clickety-clack, and tells you that no, it's impossible. Why does she say that? That's because these 4 variables are not independent. When a gas is in equilibrium, they satisfy an equation of state. An ideal gas will satisfy the equation PV is equal to nRT, where R is a universal gas constant. Its value in SI units is about 8.3 joules per Kelvin per mole. It's called a universal gas constant because it doesn't depend on the gas, whether it's oxygen or nitrogen or methane or helium. If it's behaving like an ideal gas, and when does that happen? At high temperatures and low densities, all gases behave ideally, and then this value is the same for all these gases. That's why it's called a universal gas constant. Now let's see what this lady at the shop found out. She took the pressure P, let's say 1.01 times 10 power 5, and multiplied it by the volume, which is 2 liters. So multiplied by 2 times 10 power minus 3 cubic meters. That's PV. And is that equal to, in other words, does it satisfy this equation? N is 3, R is 8.3, and the temperature is 300. Let's see. The left hand side is 2.02 multiplied by 10 power 2, which becomes 202. That's equal to, let's say right here you got 900 multiplied by 8.3. Obviously this equation is not satisfying. In other words, the laws of nature prevent you from putting 3 moles of an ideal gas at 300 Kelvin at this pressure into a 2-liter container. These 4 numbers are not independent. So the lady at the shop says, look, you know what? I can give you the same pressure, I can give you the same temperature, I can put it in this volume, but the number of moles will be much less. You say, no, I insist on 3 moles. In that case, she says, fine, that is fine, I can give you 3 moles also. R, of course, is fixed. The volume of the container is fixed. And you want the same pressure, fine, but I'll have to lower the temperature considerably. So, you can't arbitrarily choose 4 values. That's the meaning of the statement that these 4 variables are not independent. They have to satisfy this equation for the gas to be in equilibrium. Now, I want to tell you something very interesting and very important. Supposing we plunge the piston down. What do you suppose will happen? The gas right beneath the piston gets compressed. The compressed gas pushes down on the next layer pushes down on the next layer, and pretty soon a wave of compression travels down, hits the bottom, gets reflected, and goes up and down until the pressure equalizes all over the gas. Now, immediately after compression, the layer right beneath the piston is compressed and its temperature is higher than what it was before. When you compress the gas, the temperature goes up. So the temperature is also different at different points of the gas, and it takes some time for the temperature to equalize all over the gas. So in other words, for the entire gas to come to the same pressure and the same temperature, it takes a little time. During that time, the gas is not in equilibrium, it is in some kind of a flux, a turmoil. When it finally comes to an equilibrium, the entire gas can be described by one number, the pressure, one number for the temperature. In other words, the gas can be given a pressure value and a temperature value only when it is in equilibrium. When it is not in equilibrium, different parts will have different temperatures, different parts will have different pressures. So when we are talking about this equation, PV is equal to nRT, we are talking about a gas in equilibrium. Now that we know that these 4 variables have to satisfy this equation, it's pretty obvious now that if I know 3 of these variables, I can use this equation to find the 4th. For example, if I know P, V and T, I can use this equation to solve for N. Or if I know N, usually that's the case, the number of moles is usually fixed and known in the beginning. So if I know N, and if I know the temperature and volume, I can find the pressure. Or if I know the pressure and temperature, I can find the volume. Given the number of moles, two of these variables will find the third. So only two variables are independent. Supposing we choose P and V to be our independent variables, we can now plot a graph. So on the vertical axis, I put the pressure. On the horizontal axis, I put the volume. Remember, the graph exists only in the first quadrant. The second and third and the fourth quadrants do not exist because the pressure cannot be negative. The volume cannot be negative. Right. So if I have P versus V, and if I put a point here, what does this point represent? Remember, the number of moles is given. So this point tells us the pressure is P1 and the volume is V1. So if I know the pressure as P1, the volume is V1, we know N. This equation determines the temperature, so I know the state of the gas. So a point on a PV diagram represents the state of a gas, the state of an ideal gas. A different point represents a different state of the ideal gas. Supposing I say that the gas goes from P1 V1 to this point P2 V2 along some path. Now you see, this path that I've drawn consists of an infinite number of points, each point representing an equilibrium state of the gas. In other words, the moment I draw a path on a PV diagram, it represents a process where I am taking the gas through an infinite number of equilibrium states, each of them being a point on this curve. Supposing I wish to compress the gas from a volume of 3V1 to a volume of V1 at constant temperature. That means if I look at the equation, PV is equal to nRT, the right hand side is constant, so the pressure is equal to this constant number. Let's say the temperature is 300 Kelvin. That's the surrounding, let's say the temperature, the ambient temperature. So I substitute number of moles of the gas, R 8.3 and temperature 300 into this numerator and divided by the volume. Now if I were to sketch this equation, pressure versus volume, you get this curve called an isotherm because the temperature is constant. So if I move along this isotherm from this initial state, 3V1, P1, to a final state, V1, 3P1. Notice that P times V is the same before and after. It remains constant because the temperature is constant. In fact, at every point along the path, the temperature is constant. I am moving in this direction. That is an isothermal compression. But here's the important thing. Every point on this graph represents an equilibrium state of the gas, and along this curve there are an infinite number of points. So that means I'm taking the gas through an infinite number of equilibrium states from the initial state to the final state. An approximation to that would be adding sand grain by grain, and each time I add a grain of sand, I wait for the gas to come to equilibrium with the surrounding temperature so that the temperature is 300, add the next grain of sand, wait for it to equilibrate with the surrounding, and so on. That way, supposing I add 100,000 grains of sand, I have got 100,000 points along which I have taken the system. So this continuous curve containing infinite number of points is actually an idealization. It represents the process of slowly compressing it so that at all times the gas can be considered to be in equilibrium or infinitesimally close to equilibrium. Such a process is called a quasi-static process. Quasi-static because an equilibrium is static, but then if it is static, how is it moving from equilibrium to equilibrium? So that's why it's called a quasi-static process. So in reality, we don't actually add sand grain by grain. What we do is we perform the compression very, very slowly so that this gas at all times is only infinitesimally higher temperature than the surroundings. Because as I compress it, the temperature goes up. It means that I compress the gas so slowly that at all times allowing heat to go out so that the temperature inside and the outside are practically the same. That's called a quasi-static process. So whenever we draw a curve to represent a process on a PV diagram or a PT diagram or a VT diagram, the curve represents a quasi-static process. So we are going to use quasi-static processes to do calculations in the next couple of videos. So goodbye for now. Bye-bye.